Good morning, everyone. I am Mohammad Humayan, Principal Consultant with EnerNex. We are an engineering and consulting firm based in Knoxville, Tennessee. And thank you for the EMT team for putting this up and also offering this opportunity to present. And topic of my presentation is sustained overvoltage due to zero sequence resonance for shunt compensated transmission line. As the topic indicates, it's related to shunt compensated line and zero sequence resonance. I will be following the usual outline, starting with introduction to my company, and then zero sequence resonance background, mitigation measures, and also we did some study of a large wind plant. I will share that in EMTP simulation results, and actually the mitigation technique that we applied over there, and finally summary. So at first, as I mentioned, EnerNex is engineering and consulting firm based in Knoxville, Tennessee. We celebrated our 20-year anniversary last year, and just 1 year more than EMTP. And since 2018, we are part of Case Group, which is a global company, headquartered in Milan. And we have sister company, which is under Case Group, Kima Labs, probably many people will know them. And in Pennsylvania, we have one of the largest high power, high voltage lab in North America. And particularly at EnerNex, we have two groups. One deals with power system studies of means modeling and simulations using tools, EMTP, and other EMT tools. Moreover, we also do distribution studies using OpenDSS, SIME, Synergy Electric, and others. And we also have a smart grid group that deals with grid technology consulting and grid modernization, for example, helping utilities build use cases, business cases, and setting up the requirements, help utilities procure a grid modernization system, for example, AMI, DERMS, and others. Now coming back to the zero sequence resonance background, the first question is, what is zero sequence resonance? It is a condition in electrical system where zero sequence impedance of the network creates a series resonance condition during unbalanced breaker operation, along with the source voltage on healthy phases. So for example, if you see here in this circuit, we have a source, and then there's an unbalanced circuit breaker operation. One of the phases is open, whereas the other two phases are closed. And there is a shunt reactor, and the phase to phase capacitance and phase to ground capacitance of the lines. And its equivalent resonance circuit would look like this. So phase B and C, healthy phases, and then phase to phase capacitances, and Z equivalent, which is basically the shunt reactor and the phase capacitance. So this zero sequence resonance would happen. It would be an interaction between shunt reactor, phase capacitances, disconnected phase, and energy from connected phases. I will move to the next slide. So the main elements required for this zero sequence resonances are shunt reactor, interface capacitances, and also it needs at least one of the phase should be disconnected, and at least one of the phase should be energized. And this is another view of equivalent resonance circuit, or Thevenin equivalent of this particular circuit. Are you able to see that, by the way, screen? Or I should stand here. So voltage source, capacitances, and the reactor. The question is, why unbalanced phase operation? It can be intentional or unintentional. Intentional when it is done for single phase stripping schemes are applied to improve the system reliability and stability. And unintentional operation would be, for example, if the breaker is supposed to close our breaker is supposed to open, but it remains stuck. So there would be unbalance. For example, during opening of operation of the breaker, if one of the pole remains stuck, what happens that this is an unbalanced operation. Similarly, if two pole remain stuck during opening of the breaker, it's an unbalanced operation. And likewise, during the closing operation of the breaker, if one pole remains stuck or failed to close, so we will have unbalance. And similarly, for if there are two phases are stuck, then we will have another situation of unbalanced operation. As you can see that there are different ways in which unbalanced operation can happen. So when we run the simulation on a circuit, so there would be a number of cases to run, even for a single breaker. Well, if there is a zero sequence resonance, is it an issue? Yeah, because it leads to high overvoltage, and even for short duration, it can damage the equipment. And it would remain energized and until there is an intentional action to remove that unbalance or resonance operation. Well, so there's an issue, and there are mitigation options available as well. And mainly they are classified into two categories: passive actions and active actions are mitigation options. If we look at the passive options, one would be to avoid the shunt compensation degree. It is basically means that resizing the shunt reactor such that there is no resonance condition. Or it can be dividing the compensation between the line and then substation. Other passive option would be include neutral grounding reactor, which is basically is going to detune that resonance point. And also neutral resistor can be added in order to provide the damping. And there are other options as well, for example, ungrounded neutral or special shunt reactors. And each of these solution would require a careful design because they might lead to another issue. And finally, one thing would be recommended to do not do single phase switching if you want to really avoid that issue. But still, in this case, unintended unbalanced operation can happen. And among the active operation, these are basically putting special protection schemes. For example, if it is detected that there is an unbalanced operation of the breaker, so you take out another breaker, or you bypass the shunt reactor, or you disconnect the shunt reactor on particular phase. Now I move on to a large wind plant study. We did a number of simulations using EMTP. It involved line energization, transformer energization, inrush current, cab bank switching, and also TRV, harmonic studies using EMTP. However, this presentation is only about zero sequence resonance. And by the way, this was the first time we ran this study of zero sequence resonance. This is a simplified snapshot of EMT modeling setup that we had. 500 kV is the point of interconnection for the project. It is reduced to 345 kV using transformer. And we also have 80 megawatt shunt reactor in at the substation, and 80 miles of 345 kV line. And then there are MPTs for wind plants and also the wind plant model. Overall, we ran 56 different scenarios, which included a single or two-pole unbalanced operation, not only for closing, but for opening as well. And those were related to switching of the breakers for 345 kV line that you see over here, and shunt reactor breaker, and also main power transformer of the wind plant that is not shown here. And 18 of those scenarios were initial base scenario in which we energize this line or different components, and we look at whether there is any zero sequence resonant condition or not. And we found that there was one case. And that's why we applied this passive scheme by using 30% neutral grounding reactor and rerun all the cases. We had to rerun all the cases because it is also important to look at whether addition of this shunt reactor or neutral grounding reactor is creating another issue or not. And moreover, we also performed simulation of de-energization in which we assume that system is working fine, and then we take out, for example, MPT and then the line to observe that whether there are other issues. Yep, so one of the cases that generate zero sequence resonance condition in our circuit was when we energized this 80-mile line along with this shunt reactor using this breaker, and one of the pole remains stuck. And in our simulation, we assume that phase C is stuck. I will move on to the next slide. So this is voltage, a steady state voltage at 345 kV side of wind plant. Phase A, B, C, blue, green, and red. Blue and green phases, you see that its peak is around 1 per unit, so it's fine. However, due to resonance condition on the pole that was stuck, we see that it is significantly higher because of resonance condition. In fact, it's a little bit more than 2 per unit. And even this operation for 1.4 seconds in EMTP simulation resulted in arrestor duty beyond its capacity. So it was very important to put a mitigation option for the project. And by the way, for the rest of the cases, we didn't see any issue. So we applied 30% neutral grounding reactor and reran the simulation, and you can clearly see that now the red phase voltage is pretty small. And also the addition of this neutral grounding reactor did not introduce new resonance conditions, so which was good. And also de-energization cases, we didn't notice any significant issue with any of the cases. And after running this EMT simulation, we also thought about whether there is an active mitigation strategy that we can apply. Because of configuration of these breakers, we came up with one. So the strategy was, when we energize this line, we should energize shunt reactor after making sure that this line has been energized well. So it means all the breakers are closed. So this was one of the steps. And number two, when we open this line breaker, we will also open this breaker A2 to make sure it will have high probability that these both the breakers would have malfunction. So it reduces the risk of resonance. Yep. So in summary, we looked at zero sequence resonance and also mitigated it using a passive and active measures in our project. Thank you very much.